All right, so in this video, we're going to talk about lessons 5 and 6. Lesson 5 was 3D moments, and lesson 6 was couples. So 3D moments are pretty similar to 2D moments in that they cause a body to rotate. However, your approach is pretty different, actually. So there's really no way to do this trigonometrically. You have to do it with coordinates. So looking at the steps to solving the problem, instead of just doing the perpendicular distance times the magnitude of the force, now you have to look at like unit vectors and force vectors and all that. So step one would be to calculate the force vector. And to do that, you find the direction vector from like moving in the direction that the force is going. So you start with whatever your point near the head is, and then it's head minus tail for all three directions. And then that is your position vector. But again, we need to find the unit vector because if you multiply the magnitude of the force by just the direction vector, you're going to end up scaling the magnitude of the force, which you don't want to do because then it's not an accurate representation of how much it's twisting or spinning, I guess. So the second step would be to find the magnitude of the direction vector so that we know what to divide it by and get a vector with a magnitude of 1. So here you use essentially the distance formula. So you just square each one of these components and then square root the sum of that. And then to find the unit vector, you divide your position vector by the magnitude of that vector. And then you'll get a vector with the magnitude of 1. And if you wanted to check that, you could do this step again, but instead of using the regular position vector components, use the unit vector components, and then it should simplify to 1. So once you have your unit vector, you're essentially just, think of it as like a conversion factor, but between, not between like units, it's between a scalar quantity, which is the magnitude that you're given in the problem, and the vector quantity, which is what you're going to end up cross product or putting into your cross product. So that's your force vector. All these steps were to just get your force vector. And then you're going to find a position vector describing the perpendicular distance between the moment and the spot that you're taking the moment about. And then you're going to take a cross product of those two vectors. So first of all, it's important to know that when you're crossing two things, so you're crossing, or the formula for a moment is r cross f, so the position cross the force vector. But what is important to know is that cross product, these are not interchangeable. So if it's r cross f, you have to make sure that you're doing r first, or r in this middle row here, and f on the bottom, because since it's subtraction like everywhere, you're going to end up doing the math wrong if you swap them. So that's an important thing to know, is that you have to do it in that order. So from the previous slide, we have a position vector with 3 terms and a force vector with 3 terms. And again, it's r cross f, so r, so you put your dimensions ijk at the top of the determinant, and then the next one, the next row, is your ABC for your position vector components, and then the bottom row is your force vector components. So then you go in and cross product that, right? So if I'm finding the I component, I'm going to ignore this whole column. I'm going to ignore entirely the I column. And then you essentially just do top left times bottom right minus top right times bottom left. So you literally draw across these two columns that you have left. So it's top left times bottom right minus top right times bottom left. And you do that for every term. So since I'm going to do the J components now, I'm going to ignore this column so that my top left will now be A, bottom right will be F, minus top right will be C, and bottom left will be D, right? And then you do the same with K. So a couple important things. Like I said, you just cover the column for the component that you're looking at, and then it's just this direction minus this direction. But then another thing that people forget a lot is that in this formula, there's an inherent negative sign in front of the J because of right-hand rule. I'm not going to try to explain that in the PowerPoint because I can't show my actual hand. So if you have questions on that, please come to office hours, but I will absolutely explain it if you need me to. Okay, so moving on to couples. So a couple is a pair of forces of equal magnitude acting in opposite directions. So that means that anytime you're looking at a problem and you see two lines that are parallel to each other, you should automatically double check if their magnitudes are equal and if they're acting in the opposite direction. Because if they are, that means you don't approach it like a normal force or like a traditional force, you approach it as a couple. So another important thing to know is that couples are moments, right? So a good way to think about it is put your pen on your desk, and when it comes to it, flick almost, or like poke your pen at the clicky part away from you and at the tip towards you, right? So automatically that pen is going to start to rotate, right? So that's just a proof really quickly that couples are moments because those two forces applied made the pen rotate, which is the definition of a moment. So because it's a moment, the same equation can be used, but instead of this m, it's now going to be c. So m becomes c. So then it's c equals the perpendicular distance times the force, which also means that this equation is still relevant. It's just a matter of making sure that you're using it in terms of the new changed variables, because I think these variables are slightly different between the two, or at least the way my brain sees them is they're slightly different. So d perpendicular, instead of being the distance between the force causing a moment and the place you're taking the moment about, so that's what it was back here. Oh wait, this is the 3D one. Anyway, so instead of being the traditional d perpendicular for the moment, now it's the distance between the couple components. So the distance between the two arrows. And then F is going to be slightly different in that it is the magnitude of the couple. But a lot of people tend to lean towards summing the forces of the couple, right? So there's two forces, but you only take one of the magnitudes. So if the forces are both 200 newtons, then the magnitude of the couple is 200 newtons, not 400. So you don't add the two forces together. And I thought this was hilarious, so I figured I'd add it there. So another thing that kind of gets a little tricky is d perpendicular sometimes. So if you're lucky, it'll be given to you in the problem. So all of these forces in this example, which is worksheet 1, I believe, for a two-dimensional, these were all in the exact plane of the x and y axes, right? So this translated right up to here, and this point 2 translated right between there. Obviously, it was labeled, but this 5 was labeled right as it is. So those are basically given to you. Other times, it's going to be a little trickier to find that distance because you're going to need the trig relationships or the angle relationships. So just remember that when you're finding that, you're essentially just finding the horizontal and vertical components of each of the forces and finding the difference between the two. The distance between the two, not the difference. So a quick reminder, if you're given a slope triangle, you have to use the side ratios. And if you're given an angle like this, like the actual 30-degree angle, that's when you use SOHCAHTOA. And then last but not least, couples, like everything in the world, can happen in 3D and do happen in 3D. So it's almost solved exactly how a 3D moment is, right? The difference being just that position vector. So steps to do this, you find the force vector, and if you need independent steps like written out, look at slide 2, but I'm going to go through this example really quickly. So for the force vector, that's Q. So I'm looking at Q and S are the couple because they're opposite in direction. They were both 50 pounds or newtons, I don't remember, but I cropped it out um, just to save space. But yeah, so those are both 50, acting in opposite directions, and they're parallel to each other. So they are in fact a couple. So to find the force vector Q, you can either find Q or S. I chose Q just so I could write it up here. Um, you find the position vector, which is from B. So Q is going from A to B, so then you do B minus A. So that's how I got this. Then you find the magnitude of that position vector, so I know what to divide it by. And then seeing as if I square everything and then square root it again, it's just going to be the 12. Then I just divide all three of these terms by 12, so I get 0, 0, negative 1. Again, quick check, if I square all of these and then square root them, I end up with 1. So that's boom, that's what we want. Unit vector is a magnitude of 1. Ah! And then I multiply my given magnitude through that vector. So 0, 0, negative 50 for my vector. That's my force vector Q. And then the second step is find a position vector from any point on the line of action of force Q, which is from here to here, to the line of action of force S, so from H to G, right? So that means I could go from A to G, I could go from G to A, I could go from A to H or H to A, I could go to B to H or H to B or B to G and G to B. So it doesn't matter. I just chose these two because it's the front of the box and I don't know why I chose them. But you can choose any of them and you'll get the same answer. So in this case, since I'm drawing my vector from A to G, it's going to be G minus A. So that landed me with 4, negative 3, 0. And then that is my position vector. So R cross F, which actually turned into R cross Q because it's force Q, looks like this. So it's the 4, negative 3, 0 times 0, 0, or cross 0, 0, negative 50. I moved those down here where they belong, did the cross product out, and ended up with this. So it's fairly straightforward. You just need to get practice, and I would do that by doing the homework because, as you probably saw from quiz 1, the quiz questions are very similar to the homework questions. And then a quick reminder, my office hours are Monday, Wednesday, and Thursday from 5:30 to 6:30, and then Tuesday and Thursday from 9:15 to 10:15 in the morning. Bring homework questions, bring content review. We can just hang out if you want. I don't care, but I'm going to be there, so come visit. And that is it for lessons 5 and 6. I will see you in class.